Okay, Assalamualaikum guys, good morning, evening, and afternoon. Okay, so today we'll be talking about friction. Alright, so yeah, it's about friction from your chapter 8 of the statics course. Okay, so we'll be talking a bit about friction first of all. So I like to refresh your mind about the stuff that you've learned in high school. So let's say you're on a grassy patch, okay? So I'm just gonna yeah, label this as grass, right? Grassy patch. Alright. And you are pushing a box, for instance, okay? You're pushing a box right away. Okay. You apply a force, and this force let's just call it as P. Okay, you apply a force P, okay, that's pulling the box rather, alright? As you're pulling the box, okay, with force P, alright, you'll notice some sort of like a resistance. You feel like, oh, there's sort of something that's, counteracting to the force that you're pulling, okay? And this resistance isn't really a shocker because it's quite common when you are applying a force, okay, on an object that is touching the surface, and this force we call it as a frictional force, okay, or I'll denote it as F. Alright, so we call it as frictional force. Right, frictional force. Okay, and the thing about this frictional force, right, is that it opposes motion, okay? It tends to oppose motion. That's the nature of frictional force. Alright, it opposes motion. Okay. And how it opposes motion, it actually depends on the surface itself. Rather, it depends on the surface itself, okay? Whether the surface is rough or smooth, okay? And if the surface, for example, was rough, right? If let's say it was very rough, then uh, the frictional force would be much higher, okay? That means your F would become much higher. But if the surface was smooth, okay, if the surface was smooth, then the frictional force would be lower, okay? And how do we know whether the surface is related to the frictional force? And this is also you've learned in high school as well, okay? So we know that our box, right, of course has a mass, right? And if something has mass, clearly it will also have weight, because weight is basically mass times g, okay, gravitational acceleration, and we know that g is 9.81, okay, meters per second squared for the case of Earth. Different planets, different g, okay? And the thing is that once we have g, okay, once we have weight, once we have weight, we have a force that is exerted by this grassy patch, okay, to the box itself, okay? It's exerted the grassy patch to the box itself, by the grassy patch to the box itself, okay? And this force is what we call as our normal force, okay? I denoted as N in gray color, so what we call it as normal force, okay? So this normal force is actually related to friction itself. There's a relationship, and we know this relationship actually is F is equals to U N. Okay, what is this U? This U is related to the surface itself, and we know it as the coefficient of friction, okay? The coefficient of friction, okay? Sorry, not fraction, it's friction, okay? Coefficient of friction, right? And this value, okay, it depends on the surface roughness. So if the surface is very rough, that means that your U is very high, okay? Which of course, if your U is very high, your F also will be very high. And if your U is very low, okay, your U is very low, your F is very low. It's basically a directly proportional relationship. Your n itself would stay the same. Okay, your n itself will stay the same because your n is equivalent to the weight of the box. Because remember, in this case, right, if we're considering a two-dimensional case in terms of x and in terms of y, all right, the only forces acting in the y direction are just your weight and your normal force, right? And since the box isn't moving up or down, right, it's not moving in up or down, so your summation of Fy, okay, if you take your up to be positive, is 0. Okay, so we need to say that your n minus w is equals to 0, and of course your n just equals to w. Okay, that's should be very clear. And this is what we've learned in high school so far. Now, I'm going to extend the concept a little bit for this case of statics. Alright, so let me just erase this stuff. Okay, real quick. Okay, so here's the thing actually. Your frictional force, as we mentioned earlier, is related to P, right? It's related to P actually. Okay, so if I were to draw a graph, okay, I'm going to draw a little graph by the way, relating to P and relating to F. Okay, so you know, if you apply P, right, let's say you apply a force of P, okay, it will be equivalent to the force of F actually. Okay, since in the case of statics, our summation Fx also is 0. Okay, I mean the box is not moving. Okay, so that means to say that your P minus F is equals to 0, which is leading to the fact that your force P equals to frictional force F. So if we draw the graph, okay, you'll see a directly proportionate relationship between P and F. Okay, until it reaches a certain point. Okay, and what happens next is that eventually as P increases, your F will decrease and will become a highly non-linear relationship. Okay, so the first part here, okay, the first portion of this graph, it's clearly a linear relationship. Okay, so this is clearly linear, and after that particular point of interest, what happens next is that it becomes non-linear. Okay, it becomes non-linear. So what is going on actually? Why is it if P reaches to a certain point, the F also reaches a maximum, and it's the end of the linear characteristic before it transitions to non-linear? Why is that the case? Well, the thing is, as P reaches a certain point, the frictional force, okay, or rather I call it the static frictional force, reaches a certain point, which we call it as F max. Okay, so the static frictional force by right is basically the maximum frictional force that allows the object, okay, or in our case the box actually, to remain stationary on the particular surface, on the surface. All right, so that is what we call as F max, our static frictional force. Okay, and if the load P is further increased, okay, so the load P is further increased, or you know, you were to keep on applying load P, you keep on adding load to it, okay, so what happens is that then the surface cannot offer more frictional force. Okay, the surface cannot offer more friction, and the box will move, and motion occurs. Okay, so all this time in the linear region, what is happening is that the box is actually not moving. Why? Because each time, let's say for example your value of P is 1 Newton, your value of frictional force is 1 Newton. It's like static this whole time. It's not moving at all until it reaches a certain point where your value of P is equivalent to F max, the maximum static frictional force, right? Which allows the object to remain stationary on the surface. If you increase the P, right, the loading force, then of course the object will start to move because your F will decrease, okay, it will start to decrease, okay, which exhibits this non-linear relationship, and your box will move, okay. So that means to say that your P minus F is no longer equivalent to 0. Whereas for the linear region, it is where your P minus F is always equal to 0, and that's why it allows you to have P equals to F. Okay? So that's the idea between the linear region and the non-linear region. And how do we know when is this F max? How do we know how to find this F max? So this F max, basically, okay, this F max is basically your what? It's basically U S times N. Okay, and US already discussed earlier is a coefficient of friction, but it's not just the coefficient of any friction, it's the coefficient, okay, of static friction. Okay, the coefficient of static friction. Okay, and like I said before, US depends on the surface itself. Different surfaces have different values of US, and in this end we already know it's basically a normal force, right? And the relationship is that the normal force equals to weight for our case, by the way, yeah, because we can see that on a flat surface the only forces acting in the y direction, right, if you were to take your x and you take your y, so the only forces acting in the y-axis are your weight and your normal force, right? That's why your normal force is related to weight. It depends on your free body diagram. I don't want to say that normal force equals to weight for all cases, right? Because let's say if it's a slope, you're dealing with a slope, right, and your body is here, okay, then the weight is obviously gonna be acting downwards here, right? But your normal force would be acting here, right? It would be acting on the surface itself. So you see, the normal force is not really equivalent to weight, but rather it's equivalent to a component of weight. Okay, it's equivalent to a component of weight. You can call this theta. So it's more of the normal force equivalent to I'm gonna draw this here. I'm gonna draw this right here. It's equivalent to, so this is theta, also this is theta, right? So it'd be equivalent to W cosine of theta, right? So the normal force in this case is equivalent to W cosine theta if you are on a slope, for instance. Okay, so it really depends again on your free body diagram, but yes, the general idea is that your static frictional force, maximum static frictional force, is basically the coefficient of static friction, which depends on the surface itself, multiplied with the normal force. Okay, and for the non-linear region, okay, the non-linear region itself, this force, okay, this particular force, okay, right here, is the frictional force for the kinetic case. Okay, this is, okay, let me just put a different color. I think maybe it's a bit difficult with yellow. Okay, so this is for your kinetic case, FK. Okay, and this FK, okay, which is for your kinetic case, is just simply UK times N. Okay, and UK is basically the coefficient, okay, of kinetic friction. The coefficient of kinetic friction. Okay, and this is only applicable if the object's already in motion. Okay, so this kinetic friction we can only use if object is in motion. Okay, is in motion, meaning to say that your P minus F isn't equals to 0. Alright, so for our case of statics, we're actually more interested in the linear region. Okay, we're more interested in the linear case. Okay, we're not really interested in non-linear case. This is more towards to your dynamics, which you will probably be covering in the next semester, right? So we're more interested in the linear case, so I'm gonna erase the kinetic case, by the way, right? So let's just erase it. We don't really need it. And I'm also gonna erase this as well. Alright. So now we have some more space, I would say. Okay, great. So let me redraw the graph again. Okay. Okay, so this is P, this is F for the static case. Okay, where F is equivalent to F max, right? And as we know earlier, that our maximum static frictional force is equivalent to US times N, right? And going back to our example again of the grassy patch, right? We have the box, same box. Okay, we applied the force P on it. Okay, and of course we'd have the frictional force, okay, or the frictional force itself, which is just F, and then we have the weight. Okay, so this is the weight, and then we end up having the let me label a different color. Normal force. Okay, yeah, normal force. Right. So it's a normal force. All right. So that's what we have so far. Now, what I would like you to know is that for the static case, actually, there are two scenarios that can happen. All right, there are two scenarios that can actually happen. One scenario is where the box, okay, would reach our F max, okay, and normally whenever our object reaches F max, okay, so when a body reaches F max, when a body or object reaches F max, okay, so the maximum available static frictional force to hold it reach F max. So what happens? So that is to say, we get the body is about to move, right? The body or object is really about to move, actually, because as you've seen before, okay, it's about to move. As you've seen before, actually, just if you keep applying more and more of P, right, we've already seen the non-linear characteristic, right? Basically, this is what we call as the kinetic or non-linear, right? The kinetic or non-linear, basically. All right, that means the body is already moving, right? Because clearly P is no longer equals to F anymore, right? This F is already the kinetic friction. It's already gonna move anyway, right? And in the static case, right, the static case is a linear case. We already know that. We've already seen it before. So it won't move, because every single time your P is always equals to F. all right, every single time until F max, until your P, okay, maybe your P, I don't know, I call this P naught, okay, is equals to F max. So so that's basically the maximum static frictional force. And when it reaches F max, the body or the object's about to move, and normally in your books they would say something like about to slip, okay, or something along the lines of impending motion. Okay, it's really just about to move, impending motion. And there is a case where your body or object doesn't reach F max. So body or object doesn't reach F max. Okay, so your body or object doesn't also reach F max, meaning to say that your P will reach F. So there's actually two cases that can happen in our linear model, our static case. Either the body or the object's just about to move, which is basically the common case, right? Or the body or object doesn't reach F max, where something interesting will actually happen, by the way. Alright, so allow me to explain. I'm going to erase the chart, by the way, just to give me a good idea to explain to you guys what's going to happen. Okay, so already erase the chart. So let me explain. So let's draw two cases. Okay, so we draw a box again, same box also, for both cases, by the way. Okay, and we apply a force of P on it. Okay, I'm going to apply a force of P on it. Alright, and we know that that will be our frictional force, okay, which is our F, and we know it's going to be a frictional force that is also our F. Okay, so here's the thing, right? If you apply P and it reaches your F max, okay, reaches your F max, by the way, okay, I said before that your body is about to move, okay, it's impending motion. Okay, we call it impending motion typically. This is the first case. Okay, impending motion. And in this case, right, if I have your normal force, by the way, right, so N, and this is your weight, obviously, which I didn't draw earlier, but okay, let's just put it as, I'm just gonna write it as W. Okay, so your F max, okay, your F max is just simply equals to US times N, right? Your US again is dependent on the surface itself, okay? So it's dependent on this grassy surface, by the way. Okay, what is this grassy surface? So it depends on that. Okay, so that's the first case. Now second case, okay, is basically what we call as when the body or the object doesn't reach F max. What's gonna happen? There's a second possibility here, that this object might tip. Okay, it might tip over. Okay, and you might be wondering, what do you mean by tip over actually? Okay, what do you mean by tip over? So I want you to understand that, okay, this is the weight of the body and the normal force. I think I'll use a different color here actually, so it become more distinct. Gray. Okay, so it'll tip over. What do I mean by that? The thing is, this particular body has a dimension, has a size actually, okay, and we call it as B and H. Okay, so B and H represents the dimension of this particular box. Okay, so you know, what happens is, as we apply P, and the frictional force is counteracting the object, right? The thing is, it creates a moment actually, alright? Remember couple moment? So what happens is that this P and this F, okay, will create a couple moment on the box itself. Okay, will create a couple moment on the box itself. So yeah, this is H. And why I say they create a couple moment is because we know that P and F are the same, right? The box is not moving. Remember, our summation of Fx equals to 0. It's static case. So therefore this F equals to P. So basically your moment, your summation of moment here would be P times H. We'll create a couple moment that will make the box actually go clockwise, right? And the only way to actually counteract with it is that if the W, the weight, and the normal force will create a couple moment as well. What do I mean by that? Meaning to say that if there is a distance between W, the weight of the object, and the normal force of the object, okay, this will create a counterclockwise couple moment. So we'll create a counterclockwise couple moment to counteract the clockwise couple moment. So your summation of moment will remain 0, because you don't want the box to be, rotating, right? But in order for a counterclockwise couple moment to happen, there has to be a distance between W. Okay, orange. I use orange. Sorry about that. There has to be a distance between your W and N. What is that distance, you may ask? So the distance actually is related to B. Okay, something between is related to B actually. So normal force, okay, the distance it has between the weight is somewhere between 0, okay, and B over 2. Okay, so this distance will be somewhere between 0 to B over 2. If the distance between the normal force and the weight is between 0 and B over 2, you'll be able to create that counterclockwise couple moment. Oh, and I forgot to highlight that again, W equals to N, and I think you guys already know why that's the case, because our summation of Fy equals to 0. Okay, so that's why they can create a couple moment, right? Because they're of the equal force, just different directions, right? So yeah, that's basically the idea. In order to keep your moment equals to 0, you would also want to create a opposite couple moment between W and N. But if, let's say, your P keeps increasing, okay, your P will keep increasing, all right, which will of course affect your F, eventually to the point that your couple moment will increase. Okay, that basically say your pH will start to increase as well. So what happens? Basically, as your pH starts to increase, your couple moment here starts to increase, of course your ND will also increase, right? Your couple moment here also will increase until D reaches half of the length of the body itself. Okay, if D already reaches B2, that's the maximum. And if it goes more than B2, if it goes further than that, if D is more than B over 2, right? So what happens? The box will tip over. The box will start to tip over, right? So that's basically the second case. But your P will never reach F max. Alright, your P will never reach F max, but it will tip over. Okay? So that's the second case that's likely to happen. Of course, the third case where the box itself doesn't move at all, right? And I think that's pretty self-explanatory, meaning to say that alright, so the third case, actually I forgot to highlight, box doesn't move. Okay, I think when you say body object doesn't reach F max, it either could tip or it just stays stationary. Okay, so that's the best way to put it, like that. Stays stationary. Okay, so that's what's gonna happen. But we're more interested, normally we're more interested whether it's tipping over or whether it's just about to move, impending motion, right? Just before it actually moves. Okay, so this is what we're mostly interested in, right? So how do we approach problems, friction problems? Okay, so let me explain it in more clear detail. I'm gonna erase this. Okay, so to approach a problem, let's say for example we're going back to our box example again, and I'm going to give some parameters to it, right? So this is our box. Okay, let's say the box has a weight of 100 Newton. Okay, right? And you're applying a force, okay, of P equals to, let's say, about 20 newtons, right? So we know that the coefficient of static friction, and normally this is given to us because for this grassy patch, okay, is about 0.25, right? And what else I have to give you? Okay, yes, the dimensions of the box. What are the dimensions of this particular box? Okay, so the dimensions B and H. So B is about 2 meters, H is about 2 meters, okay? Right? And we are interested to know whether this box, okay, is about to move, okay, whether it is about to move, okay, it's about to move, okay, or we're interested whether it's about to tip. It's about to tip, actually, to tip. So we're either interested to know whether it's about to move or about to tip. Okay, because if we know it's about to move, obviously that means that we would be able to determine what is the frictional force, right? Which is the F max, and we can tell that's related to US times N. Okay, and if it's about to tip, then we can say that you know, basically in this case, if that means that F is not, your frictional force is definitely not equals to F max. Okay, so how do we know which is which? And here's the thing, actually, because we already given our P, okay, we already know what's our load force, P, right? So if we consider everything where our X and Y, positive X and Y, yeah, and we know that summation of Fx equals to 0, summation of Fy equals to 0, and summation of M equals to 0, right? So that's to say our frictional force, okay, I think I'm going to put it in a different color, let me put it in white, okay, is equivalent to 20 Newton, right? It's equivalent to 20 Newton, okay? And our normal force that's exerting on this box is 100 Newton, right? Because summation of Fy equals to 0 is pretty straightforward, okay? And because we know that, let's check if our frictional force is equivalent to the F max. So our F max, okay, the maximum frictional force offered by the surface is 100 newtons times 0.25, which is the coefficient of static friction, right? So it's 25 newtons. So we can clearly see that 20 Newton, our F, is less than F max. So no, the box is not about to move, right? Is it about to tip? Okay, that's a very important question. Is it really about to tip? So that means, yes, it's very likely to tip actually, but let's see if it's really the case or not, right? So, again, remember for equilibrium, our summation of moment also has to be equal to 0. So let me take the moment at this point here, which I'll call as point O, right? And we can see that the moment caused between P and our frictional force F, which I didn't label by the way, my apologies, is just simply, in this case, 20, okay, times with h, which is obviously 2 meters, right? So 20h, right? The summation of moment. And since it's going clockwise, I'm going to put negative, right? And also we have to be aware that this 100 Newton is also creating a moment as well, right? A couple moment. So 100 times, we call this as D. And remember, in order for the box to tip, our D has to be between 0 to B over 2, which in this case obviously means it has to be between 0 to 1, right? So we know that our summation of moment equals to 0, so it becomes negative 20 times h, which is 2 meters, plus 100 times D. So 100D is equals to 40. So this D is 40 divided by 100, which is 0.4 meters, which is well within the range between 0 to 1. So it's well within the range between 0 to 1. So it complies this particular range, which is meaning to say that yes, the box is about to tip, okay, and in order to counteract the tipping motion, the distance between the weight and the normal force is 0.4 meters, which again is within the dimension between 0 to 1 that prevents it from tipping, right? So the box isn't about to move, but it's about to tip. Okay, so you have to assume actually which case is it gonna be. Is it about to move or is it about to tip? Okay, and how do we know which assumption is correct? How do we actually know which assumption is correct? So the only way we can know whether which assumption is really correct is like this. Okay, so for the first assumption, if box about to move, okay, if box is about to move, right, that means your frictional force must be equivalent to F max, okay, which is basically US times your normal force. This is the main criteria it has to achieve, okay? And if the question actually only mentions the box is about to move or uses the terminology like about to slip, okay, about to slip, or like impending motion, okay, impending motion, or maybe it says maximum force to hold before it moves. So there's many ways they can phrase this, right? But if they explicitly stated about this kind of phrases right before it moves, okay, if they stated something like this, about to slip, impending motion, or maximum force to hold before it moves, or maybe they can say minimum force before it slips, minimum force to make it slip, okay. So there's many ways they can phrase this, okay, and if it's something along these lines, then we know the box is about to move, and we can take into the assumption that our frictional force is always the maximum static frictional force, which is just us times the normal force. But if, let's say, the box is about to tip, right? So if it's about to tip, that means to say that your F is clearly less than F max. And if your F is clearly less than F max, so the distance between the weight and the normal force, alright, has to be within 0, okay, and half of the length of the body itself, okay? So that's basically the condition to satisfy if it tips. So you have to assume normally for friction problems, whether you can assume the first case or the second case, and then you draw your free body diagram and then you solve it for the first case. And if the first case this is not satisfied, then you have to assume the second case and solve it and find the frictional force. So the only way to appreciate to that is like through problems, which I will be doing in a separate video, and later you guys can appreciate actually how to approach frictional problems. Alright, basically it involves like either following two assumptions if it's not explicitly stated. And if the question, like I said, explicitly stated like this, the box about to move, and they use this the phrases like about to slip, impending motion, maximum force to hold the object or hold it before it moves, minimum force to make it slip, they can use about these phrases, and then we already know the box is about to move. We'll always go with the first assumption and it should be no problem. But if they don't mention it, then you have to assume that tipping is also a possibility as well, where the frictional force is clearly less than F max, and the distance between the weight and the normal force, okay, has to comply between 0 to half of the length itself. Alright, because you know the weight's usually at the center of the body, so yeah, that's why between half of the length itself. Alright, so with that, I'd like to end the video. I will see you in the next video, guys, for solving the problems. Assalamualaikum.